Here's review 2, and here we start out with the eggs. Now, part A is simply old Unit 1 stuff, okay? And they tell you the population mean. What's the population? These eggs produced by this company, okay? So we're not talking a sample, we're talking a population. And the eggs produced by this company, the Babcock Company, they have a mean weight of 60.7 and the standard deviation of 3.1. So this is quantitative data, and we have population parameters. Now the only question is, a given egg, what's its probability it's bigger than 62 grams? So we draw the normal circle because we have a normal, we're told it's normal. 60.7 is in the middle, 62 is to the right, and then we're going to find the z-score. Z is going to equal 62 minus 60.7 over 3.1. The z-score is approximately 4.419. The probability that the z is bigger than 0.419 is 0.338, and of course we're doing second vars, normal CDF, 0.419, 99, and there's our 0.337 rounded to 0.338. Okay, so what's the probability? 0.338 that you'll get an egg that's 62 ounces or more. Now, what about a dozen eggs? Well, now we've got a sample. So we've got to talk about these guys together because we've got a bunch of eggs together. So if we want to use the sampling distribution of mu and sigma over the square root of n for a sample, then we got to go through the preconditions. We got to assume random and independent, that the dozen eggs are random and independent. 12 is less than 0.1 of the population of eggs. And the population is normal. Therefore, the sample size can't be too small. Okay, so that's really important. Okay, the population is, that word is normal. So the sample size of 12 can't be too small. Okay, so a dozen eggs has a sampling distribution approximately normal, mu sigma over the square root of n. So that's 60.7, 3.1 over root 12. So what's the probability? Well, the z is going to equal 62 minus 60.7 divided by 3.1 by the square root of 12, which is 1.452. And the probability that that z-score is greater than or equal to 1.452 is about 7.3%, or 0.0733. Now, the next question is about a dozen eggs. Now, we're not taking them as a sample. We want to know what they total as. We're not talking about the mean of the sample. So in other words, the average. That would have a sampling distribution. Now we're talking about the distribution of a dozen eggs taken together total. So the average is going to be 12 times 12 times 60.7, which is 728.4. The standard deviation is going to be the square root of n, square root of 12 times the standard deviation times 3.1. That's 10.74. And then I simply lay it all out, in which I put, sort of very hard to read, 7,284 in the middle, and then here's 1 standard deviation, 2, and 3, in which I'm adding 10.74 to 728.4. And then here's negative 1, negative 2, and negative 3. All right. And so there's and you can see I've got from here to here is 99.7. In other words, from negative 3 to 3. And this is negative 2 to 2. And this is negative 1 to 1. 95% and 68%. All right. The good old normal distribution. All right. Now, enough eggs. So you want the margin of error to be 0.02. So how many eggs do you need? And you want a 95% confidence interval. Okay, how do we know that? 95%. Okay, and you want the margin of error to be 0.02. So the margin of error equals z star times the standard error. Well, z star is 1.96. The margin of error is 0.02. Now, we're told that hens lay eggs 3 out of every 4 days. So their productivity is 0.75. So they want to have a confidence interval with the margin of error for the production rate. Okay, so they know that it's not every 1 a day, it's 0.75. So 0.02 is equal 1.96 times the P times Q over N. So 0.75 times 0.25 over N. And now you just do the algebra, divide both sides by 1.96. And then multiply the left side by the square root of N, and the right side, divide the right side by 0.02 over 1.96. It's a screwy looking fraction, but you can do it all on your calculator. N equals the square root of 0.25 times the square root of times 75 divided by 0.02, 1.96 squared. Let's see if we can do this in the calculator, all in one calculation. So we're going to open parenthesis. We're going to take the square root, 0.25 times 0.75. Let's close that. And now we're going to divide this, and let's open up another parenthesis to keep the denominator together. 0.02 divided by 1.96, close the parenthesis, close this, square it, and we always round up, so we're going to get 1,801 eggs are needed to have a 95% confidence interval with a standard error of 0.02. Perfect pitch. Okay. A recent study. All right, we went through this. Found 7% of non-Asians and 32% of Asians have perfect pitch. A test of the difference finds a p-value. Look at this p-value. It's really small. 0.0001. That's 1 out of 10,000 is the probability that this difference would occur randomly, assuming that there is no difference. Okay, the null hypothesis. The proportion of Asians with perfect pitch minus proportions of non-Asians with perfect pitch, that is P delta, the difference, and we're saying that's 0, that the difference, even though any idiot can see that it isn't 0. But anyway, we're doing the test. The alternative hypothesis is that the difference is greater than 0, that more Asians than non-Asians have perfect pitch. So with the interpretation, the p-value of 0.0001, we reject the null hypothesis. There is evidence that Asians have a higher proportion of perfect pitch. Now, the guy wants to say it's all genetics and everything. Sorry, Charlie. Cause and effect cannot be derived from an observational study, which is what that is. Okay? This is, you just collected a bunch of data, and you see if the people have perfect pitch or not. There is no controlling variables. There's nothing going on here. There's no experiment or anything like that. Okay, so forget about it. All right, cheating. All right, so we wanted to know, create a confidence interval. All right, so we're going to check the conditions. We were told sample is random. No reason not to assume students are independent. 4,500 less than 0.1 of the population. 3,300, that's NP, is greater than or equal to 10. 1170, that's NQ, is greater than or equal to 10. Since the preconditions are met, P hat has a sampling distribution approximately normal of 0.74, square root of 0.74 times 0.26 over 4,500. The standard error is going to equal square root of 0.74 times 0.26 over 4,500, or 0.00654. Z star is 1.645. That's the for the confidence interval. And so the confidence interval equals 0.74 plus 1.645 times 0.00654. So we are 90% certain that the true proportion of high school students who cheat is between 0.729 and 0.75. Now we're going to interpret the level of confidence. 90% of all similar samples use the CI that contains a true proportion of high school students who cheat. Okay, now if we had a 95% confidence interval, the Z-star would be 1.96, bigger, so the confidence interval is wider. All right, so that's it. Let's move on. 26. All right, now you can read this. Stop it if you want. So you're going to write the hypotheses. The null hypothesis is the proportions of people that smoke is 30%. Now look, back in 99 it was 34.8. Okay, now they start this program in 2010 to lower the rate of smoking. They want to reduce it by 2010. So they hope to achieve a reduction to 30% by the end of 2001. Early in 2002, they released this research study in which only 28.5% of this huge sample, 10,000 high school students, said they were smokers. Is this evidence that progress towards the goal is on track? All right, so the null hypothesis is not going to be 34.8 because we passed that a long time ago. For the null hypothesis, we're going to use that 0.3. So the proportion of high school students who smoke, the proportion of smoke is 0.3. P-hat is 2.285. Okay, we are told the sample is random. We have no reason not to assume independence. 2908, that's NP, is greater than or equal to 10. 7296 is greater than or equal to 10. 10204 is less than 0.1 times the population. So P-hat has a sampling distribution of approximately normal, 0.3 times 0.3 times, and with the square root, standard, so 0.3 as the mean, and the standard deviation of 0.3 times square root of 0.3 times 0.7 over 10204. Standard deviation of p-hat is approximately equal to 0.00454. The z-score equals 0.285 minus 0.3 over 0.00454, which is approximately equal to negative 3.3. The p-value of this z-score is 0.000483. With p-value so low, we reject the null hypothesis. There is evidence that the proportion of American teen smokers has declined. If I'm wrong, I made a type 1 error. The proportion of smokers has not declined, but I have concluded that it has. So I'm concluding that my measures to make it go to, to get it to reduce are working, and in fact, they're not. Okay, so CDC, they keep really good stats, say that, so this is a population parameter. 0.3 of teenagers smoke tobacco, down from a high of 38% in 97. A college has 522 students in its freshman class. Is it likely that more than 40% of them? Okay, we have population parameters. Now, we're going to use a sampling distribution with these population parameters because the sample is the 522 students. Okay? Now, we want to use the normal model. I didn't go through the preconditions. Let's run through them. Okay? Well, see, actually, well, all right, let's just do the preconditions. Here's what we can do. 522 is less than 0.1 of freshmen. And now, I guess we're going with 40%. So 40% of NP, 40% of 522. Let's go with that since that's our target number. Okay, so 0.4 times 522 is 208.8. We'll round it up to 209. So 209 is greater than or equal to 10. And then we'll do 0.6 times 522. So that's, so we got 313. That's greater than or equal to 10. Okay, so it's not too big, not too small. We're told it's random. All right, we'll assume random and independent. All right, so here's so we're going to say the sampling distribution, SD, sampling distribution, is approximately normal, 0.3 with a standard deviation of square root of 0.3 times 0.7 over 522. And so the standard deviation is 0.02, and the z-score is going to be 0.3 minus 0.2, 0.4 minus 0.3 over 0.02, which is 0.1 divided by 0.02, which is approximately equal to 5. So the p-value, so what's the probability? That 40% of them are smokers. It looks quite low.